All right. Hello out there. Great to see you. I am Sonia and I love science. I wonder about everyday things and I let my curiosity lead me down a learning pathway. So, on behalf of CK-12, let's do some science, ask some fun questions, and travel down a learning pathway together. Alone, but together. So we've been exploring electricity and magnetism. In our last live session, we explored electromagnetism. And today we are going to wrap it all up with light. Now you might be asking, what does light have to do with electricity and magnetism? Great question. You're staying curious out there. Virtual elbow bump. Whoop, whoop. All right. Light is actually a wave in the electromagnetic field. Yeah, a wave that looks really similar to a wave in the ocean. These electromagnetic waves are produced when moving charges emit or absorb energy in space. That is a big idea we will explore today. So what do you think of when you hear the word light? Maybe sunlight, rainbows, a light bulb? Well, the term light actually describes all forms of these electromagnetic waves, not just visible light. In fact, most of the light in the universe is invisible to us. All these electromagnetic waves of light have different wavelengths and frequencies. And the reason for this is they have different amounts of energy. That is another big idea we will come back to in this lesson. Okay, so we have organized the different types of electromagnetic waves in order of their energy in what we call the electromagnetic spectrum. Now, the spectrum is just a fancy word for ordering something. So have you ever like lined up in your class from shortest to tallest for a picture or something like that? Well, that's kind of how we line up the types of light waves in the electromagnetic spectrum, from least energetic to most energetic. Now, because most light is invisible, think about that statement for a second. CK-12 has created this really cool simulation that makes the invisible visible. So let's play around with the electromagnetic spectrum and launch the light wave sim. I'm going to share my screen here with you. And we are going to hop on CK-12's homepage, right? Try it again. There we go. Boom. Okay. No place like home, right? CK12.org. Got the shirt on. Okay, I'm going to scroll down to the beautiful, iconic Golden Gate Bridge, simulations, and click there. This is our sim browse page, and I'm going to type in light wave. All right, rainbow. Makes me feel happy. Okay. Are there colors we can't see? Now I hear you at home saying yes, right? Okay, I'm going to scroll for this one through the intro video and just start off in what we call the sandbox, okay? Inviting us to jump in, play around, and discover new things. Okay, so I'm going to hit the play button. Ready? And we are going to see that first big idea play out. Moving charges create waves in the electromagnetic field. So this is what I want you to think about, okay? So I'm going to move this up here and do it one more time. All right, moving charges create electromagnetic waves. So the blue here are waves in the electric field, and the red here are waves in the magnetic field. So these together make up the electromagnetic field, okay? Now, there are a few fundamental properties of waves that we can manipulate here with our sliders. The first is the frequency. So here you could see the oscillation frequency slider. Oscillation frequency, again, is just a fancy way of basically saying how quickly the charge bounces up and down, oscillate up and down, bouncing up and down, okay? And the other slider that we can manipulate is the wavelength. Now, the wavelength of a wave is how we measure it, right? Length of the wave, wavelength. And basically, you pick one part of the wave and you see where that part repeats. So I usually pick the peaks of the wave or the crests. So from one peak to the other, I will call one wavelength, to where one wave repeats itself is a wavelength. So peak to peak or trough to trough. Okay? So let's play around with the frequency slider to start us off. So I am going to observe this frequency, right? It was at 1.89 e to the 20th. Okay. Now I'm going to increase it and see what happens. So if I increase the oscillation frequency, what should happen is that charge should bounce up and down much more quickly. Let's see. Ah, it does. Now, what other things do I observe? It looks to me like the wavelength has shortened, right? Let's try it one more time. Increase the frequency further, decrease the wavelength, and it looks like I have more energy, right? So these are all observations that I can make. This illustrates the big idea we discussed earlier. All of these electromagnetic waves have different wavelengths and frequencies. And the reason for this is that they have different amounts of energy, right? So here I'm going to say low frequency, okay? Low frequency, longer wavelengths, lower energy, all right? And I'm going to make the determination here. High frequency, whoa, look at that guy go. Shorter wavelengths, much more energy, okay? Now, we use this information to categorize the waves in the spectrum, and you can see the electromagnetic spectrum at the top here. I'm gonna zoom in a little bit just so you can see this electromagnetic spectrum more clearly, but we're gonna lose sight of those sliders just for a moment, okay? So hang with me. All right. On the far left of the electromagnetic spectrum, and you can drag the cursor there to the far left to radio waves. And you can see here, okay? Radio waves. Yeah, you might say, what? Radio waves? Radio waves are light waves, not sound waves. They're light waves we use to produce sound waves, to make sound waves, but radio waves are actually light waves. They are the longest waves and they have the lowest frequencies and the least amount of energy. So they're over here on the far left side of the electromagnetic spectrum. Now, radio waves can be as long as a football field or even longer. And they're not just used for radio. They can be used for TV broadcasts or cell phone reception, many other things. So let me just share a few fun facts about radio waves, okay? So when you think of radio, maybe you think of AM or FM stations, right? AM stations actually stand for amplitude modification. The amplitude is kind of the height of the wave, right? The peak of the wave. So we change the amplitude or the height of radio waves to make certain sound signals on those stations. Now, FM stands for frequency modulation. So we change the frequency of radio waves to make sound signals on those stations. Now, radio waves are also received by TV sets, and we take those light waves and they produce both sound signals and images in TVs. There are a lot of cool learning pathways you can go down with regards to radio waves. So definitely hop on to CK-12 after the show. We have a lot of good content about radio waves. Okay, next on the spectrum, boom, microwaves, okay? Now, probably a lot of you have microwaves at home. These waves oscillate at a very special frequency that resonate with water and fat molecules that make up most of the food we eat. So they turn electromagnetic energy into heat. So these waves oscillate at a certain frequency that cause the molecules to spin, water and fat molecules to spin, generating heat. Now, our bodies are also made of a lot of water and fat molecules, making microwaves very dangerous to us. So that's why the doors of microwaves have those gridded screens. They kind of look like cages. The holes are spaced just right so that those long microwaves become trapped inside and they just bounce around inside the chamber. They can't escape and harm us. Okay, that's kind of a fun microwave fact. All right, let's move up the spectrum to infrared light. Now, you cannot see infrared light, the same as radio and microwaves. They're invisible to us. But you can feel infrared light as heat on your skin. So when you think of things generating heat, you might think of like the sun or fire or even like body heat. Yeah, these all radiate infrared light. Fun fact about infrared light, night vision goggles, right? That's what we use. Police officers or soldiers might use night vision goggles to be able to visualize the invisible infrared light. Okay, now we're gonna move up to the visible spectrum, okay? The main thing I want you to note here is the visible spectrum is a very small part of the very large spectrum of light waves, okay? Have you ever wondered why the colors of the rainbow always show up in the same order, right? Let's say them: red, orange, yellow, green, blue, indigo, violet, right? Always the same order. It can be explained here by referring to the electromagnetic spectrum. Definitely investigate the visible spectrum of light after the show. In the cafe link below, I've put another sim and a Plix that specifically focuses on the colors of visible light in more detail. So be sure to check those out. So we're moving beyond the visible spectrum into ultraviolet light, sometimes referred to as UV light. Now, this is a higher frequency than visible light. So higher frequency, right? More bouncing, more energy. It can be used to kill bacteria in food or sterilize lab equipment. The human skin also makes vitamin D in response to UV light, which helps make us build strong bones, strong teeth, right? Now, too much exposure to UV light can be harmful to us, right? It can cause a sunburn or skin cancer. So always wear sunscreen, even on cloudy days, because UV light can actually travel through the clouds. And the way sunscreen works is that it absorbs UV light and it turns it into heat before it can enter our cells and hurt us. So be sure to wear your sunscreen. Okay, we'll move up further. Higher energy light waves are X-rays. They have enough energy to pass through our skin, but they can't pass through our bones or teeth. Those cells are too dense. So what happens is the bright images that might come to mind when thinking about an X-ray image, right? The bright images show where the X-rays have been absorbed by things like our bones or our teeth. Now, limited exposure to X-rays like at the dentist or the airports are okay, but a lot of X-ray exposure can be harmful to us because the waves are small enough and have high enough energy that they can enter our cells and cause mutations that lead to cancer. So when we take X-ray images, we usually protect ourselves. Like at the dentist, you might have worn one of those heavy aprons made of lead that protects us from the X-rays getting into our cells other than place we want them, like by our teeth. Okay, now at the far right side of this electromagnetic spectrum, we have the gamma rays, which are the most energetic of all electromagnetic waves. They are small enough and have enough energy, they can pass through every cell of the human body. And you can see here, maybe you notice the image changes, that it shows an object of comparable size. So an X-ray was about the size of an atom, right? And then gamma rays are the size of the atomic nucleus. So very small, very energetic, and very harmful, right? Because they can get inside our cells into the nucleus where our cells keep the DNA, right? But we humans are very clever, and we figured out a way to harness gamma rays and aim them at cells that we want to destroy, like cancerous cells. So we use gamma rays often to treat cancer patients. Astronomers also study gamma rays or gamma ray bursts from our universe. And this can tell us about events that happen many light years away, like the death of massive stars and many other things. So gamma rays are useful to us. Okay, I am gonna let you play around with this simulation. Um, Here's some ideas. Maybe try to determine using the sliders which type of light has the highest frequency. Okay. Which type of light has the longest wavelength? Which type of light has the highest energy? Maybe just by listening to me, you could answer a few of those, but play with the simulation and make sure I'm right, right? Which type of light has the highest speed? Oh, that is a trick question. All of these waves travel at the same speed. That's right, the speed of light. So investigate that further. As always, there are slider-based questions here, okay? And we end with 4 more beautiful, interesting, real-world examples that have big questions that carve out learning pathways for you. Here's one about those gamma ray bursts I just talked about. Look how beautiful this image is. What is a gamma ray burst? So you can go investigate that further if you're interested in astronomy. I will stop sharing my screen now. And I just want to say, I hope you have a great weekend. Thank you for joining me on a Friday. And on Monday, my friend Will, another member of the CK-12 science team, will be here to talk science with you and have some fun. So I hope you will join us Monday at 11:30. Have a great weekend and have fun with the Lightwave Sim. Thank you.